All right. Hello, everyone, and welcome back to Calculus. So this is our final video in Unit 2. Today we're talking about power series and the radius and interval of convergence such. So power series are kind of a generalized format of a Taylor series. But in general, we're just trying to represent functions in sort of a nice polynomial way. And today's goal is we're trying to mix our power series with our series convergence test and be able to figure out when those series will converge to a value. And so be a good approximation near our center point. So like I said, power series is just a more generalized term than a Taylor series. So this is going to be any series that is centered, or any polynomial that's centered at x equals a. And so we're just going to have a bunch of constants times x minus a to different powers. And that's going to be a power series about a. So again, the CNs are just constants, and x is taken to be a variable here. Sometimes these power series are going to converge for certain x's and diverge for other values of x. So for example, if we look at this series, right, so this is centered at a equals 0, and all the CNs are just 1. This is a geometric series. If we think about it, every new term is just multiplied by x from the previous term. So we took x being different numbers, we know based on our geometric series what would happen. So for example, if x is 2, then we'd be multiplying each time by 2. In other words, our R value would be 2, and we know that this would diverge. But if we took x being 1/2, then each new term would be multiplied by 1/2. So R is 1/2, and we would know that this would converge. So in total, we know that this power series converges whenever x is going to be between -1 and 1, because that's when our R value, the absolute value of it, is less than 1. And it's going to diverge whenever the absolute value of x is greater than or equal to 1. In other words, if we were using this to try to approximate a function value, we would probably only want to even attempt to use it to approximate anything in this -1 to 1 region, because we wouldn't actually get a finite function value if we tried outside of that region. Okay, so let's see an example where it's a little bit more complicated to determine the interval of convergence. And this problem tells us to use the ratio test. In general, that's almost always going to be the tool that you use, at least to figure out the main interval of convergence. We may need to use some other techniques for our endpoints, but I'll show that in an example too, what I mean by that. Okay, so ratio test on this sum. All right, so we know the ratio test asks us to take the limit as n goes to infinity of the n plus 1 term divided by the n term. So the n plus 1 term divided by the nth term in absolute value. So we want to look at that limit. And so let's go ahead and simplify this down. So the n factorials cancel, and we're left with n plus 1 in the numerator. And the x's cancel as long as x isn't 0, right? And so we're left with x in the numerator. And the absolute value of this, for any given x, so if we think about x being a constant for a moment, any different constant, the limit of the absolute value of n plus 1 times that constant, that's going to end up being infinity. Right? If x is 7, then this is the limit as n goes to infinity of 7n plus 7. If x was -5, then this would be the limit as n goes to infinity of the absolute value of -5 minus 5. In other words, just the limit of 5n plus 5. Right? So no matter what x is, our limit's going to end up equaling infinity. And if you think back for a second, ratio test needed us to end up having a having our ratio equal what in order to converge? Right, we need a ratio less than 1. Hopefully that's what we were thinking of when we wanted it to converge. And so because our ratio is greater than or equal to 1, or strictly greater than 1, we know we're going to diverge. So by the ratio test, diverges. And then going back a second, right, we need to remember this step worked when x wasn't 0. So we know our series is going to diverge specifically when x isn't 0, is what we've said so far. And then the question is, what happens when x equals 0? And if we go back to our series itself, we're looking at n factorial times 0 to n. In other words, we're summing up a bunch of zeros. So this is going to converge because it's just an infinite sum of zeros. In other words, just equals 0. So in other words, the answer to our question is just when x equals 0, the series converges, the power series converges. Otherwise, it diverges. And that is kind of the final answer that we end up seeing from our work. Okay. So that's one example. Let's do a second example. That'll be a little bit more interesting. So again, we're told to use the ratio test, and we're trying to figure out which values of x would make this converge, right? So again, kind of trying to figure out things like if x was 0, would this series converge? If x was 10, would this series converge? Yada, yada. So our goal is to use the ratio test and kind of figure out what x values would make the ratio test work. So ratio test, again, says take the limit as n goes to infinity of the n plus 1 term. So x minus 3 to the n plus 1 divided by n plus 1 divided by the nth term. All in absolute value. So I got the limit as n goes to infinity of x minus 3 to the n plus 1 over x minus 3 to the n, n and n plus 1. Okay. All right, so simplifying down a little bit. So we get the limit as n goes to infinity. N of the x minus 3 is canceled, so we get x minus 3. And then n over n plus 1. Okay, notice that x minus 3 doesn't depend on n at all, so it can actually come outside the limit. In other words, for any given x, that's just a constant, right? So we're going to bring that outside of the limit, and we'll need to bring it up with the absolute values. So limit as n goes to infinity of n over n plus 1. Limit as n goes to infinity of n over n plus 1 is just 1, by kind of turning on our pre-calc brains and thinking about our highest powers in our numerator and our denominator. So we get that limit equals the absolute value of x minus 3 times 1. In other words, we get the absolute value of x minus 3 is what we get from our ratio test. And we want our limit to end up being less than 1, right? That's what makes our ratio test converge. So for convergence, we thus need absolute value of x minus 3 to be less than 1, i.e. that tells us that x has to be between 2 and 4 to guarantee convergence strictly from the ratio test. All right, notice that I have open parentheses because I had a strict less than, so I don't want to include x equals 2 and x equals 4 yet. Okay, so that's one thing that we can conclude and we wanted. So that was part of our answer. So we need to figure out exactly where it converges and exactly where it diverges. So by ratio test, we would need that. Ratio test also says that it diverges if our ratio is greater than 1. So for divergence, we, by the ratio test, would need to have absolute value of x minus 3 be greater than 1. And so that's giving us that anywhere from minus infinity to 2 and from 4 to infinity, any of those x values, we know that our power series would actually diverge. So in other words, when we plug in x equals 10, we know that this series should diverge. Okay. And then the last thing that we need to think about is, okay, we figured out convergence and divergence for every x except for x equals 2 and x equals 4. And this is what I mean by our endpoints, is we might need to be a little bit careful about those. So that gave us sort of our main piece, and then endpoints is the other thing we need to think about. So at our endpoints, that is at x equals 2 and x equals 4. Let's think about what our series even looks like. So at x equals 2, this is the sum from n equals 1 to infinity of 2 minus 3 to the n over n. Okay, that 2 minus 3 to the n, really that's the same thing as minus 1 to the n, right? Ooh, I know this series. Which series is this? Alternating harmonic, right? And we know that that converges. Okay, so that's one of our endpoints taken care of. We didn't even need to do a test. We just knew that that series converges. And then the second endpoint was x equals 4. And for that, we need to look at the sum from n equals 1 to infinity. So 4 minus 3 to the n. So that's really just 1 to the n. So 4 minus 3 to the n over n. Again, that's 1 to the n in the numerator. In other words, it's just 1 in the numerator. And we know this is the regular harmonic series, and it diverges. So it's a p series with p less than or equal to 1. And so, okay, x equals 2 converges, and x equals 4 diverges. So that's kind of the breakdown. Was these were ratio test, and the other two answers came out of just looking back at the series. So in total, in summary, our answer ends up being that converges for x in, let's see, since it converged at 2, we get to do a closed parentheses at 2. It diverges at 4, so we want an open parentheses at 4. And that is all to the places where our power series is going to converge. All right. So I've said these words before in here, which is interval of convergence and radius of convergence. So the interval of convergence is exactly what it sounds like. It's the interval of x values where our series is going to end up converging. And then the radius of convergence is just think about the length of that interval and divide it by 2, right? Because it's a radius instead of a diameter. So we've seen some examples so far, right? So our geometric series that we saw, we knew that it was going to converge for x's between minus 1 and 1. So that's our interval of convergence. And then our radius is half the length of this thing. So this thing has a length of 2 because we're going from minus 1 up to 1. So our radius should be 1. In example 2, our series converged only at x equals 0. So this interval doesn't have any length. And so our radius of convergence is 0. And then lastly, our last example that we just looked at, our interval of convergence that we figured out was from 2 to 4. And this is a length 2 interval again, right? Because we're going from 2 up to 4, so that's a distance of 2. So our radius being half of that distance, our radius is 1. Okay. So this is the last problem here. And I want you to go ahead and pause and try this yourself. So I want you to do the ratio test and sort of figure out which x values this converges at. Be careful about your endpoints. Make sure to think about those. And then also determine the interval in the radius of convergence. All right, so go ahead and pause here and try this question. All right, hopefully you actually paused there and tried it. But I claim that the interval of convergence that you should get is from -1/3 to 1/3, close parentheses on the positive side. And the radius of convergence is going to be 1/3, because again, it's half of the length of this interval. That interval has a length of 2/3, so we should get that the radius of convergence is just 1/3. All right, congratulations. You now have sort of the full picture about series, and we will be going forward and we're going to be using a project to kind of see exactly how this ends up really helping us in the real world. Thanks, everyone.